Hello, everyone. Welcome you back to study MA4822, which is a course about the measurement and the sensing system. Today, we move on to study lecture on measurement of force. As usual, before we enter the study of today's lecture, let me give you a quick overview or review about the answer to these four common questions that you may have in mind. Question number one, why to study this course? Question number two, how to study this course? Question number three, what are you going to study from this course? And the question number four, how to learn the knowledge from this course. Let me begin with the answer to the first question, which is about why to study this course. By now, you should know that our mission on Earth includes, number one, to understand the world, number two, to improve the world, all right? Then how to understand the world? Then we need to discover knowledge. How to discover knowledge? We need to have sensory data. How to obtain sensory data? We need to make use of measurement and the sensing system, all right? Then how to improve the world or how to change the world? The answer is to invent smart products, smart systems, smart machine. Then how to invent smart products, smart machine, and the smart system? The answer is to incorporate closed loop feedback control system inside this system, this product or this machine. Then how to design or construct closed loop feedback control system? The answer is to make use of sensory data in order to close the feedback control loop. Then how to obtain sensory data? Answer is to make use of measurement and the sensing system, right? And from this slide, you will see in industry and in society, there are many places which need to have intelligent system. For example, we may want to have a smart parking system, smart street lighting system, smart building system, smart home system, smart environmental system, smart healthcare system, etc. So therefore, this course is extremely important, right? In order to support our mission for the understanding of the world, and also support our mission for the improvement or change of the world, right? The second question that you may have in mind is about how to study this course, right? So my advice to you is to put yourself into the mindset of a designer. Then with the keyword of a design or designer, automatically you will ask yourself these four questions. Question number one, who are the user? Question number two, what are the needs from this user? Question number three, what should be the functionality of your product or your system that you are going to develop in order to meet the need of this user, all right? Question number four, what should be the solution behind the design of your system or your product, all right? So the answer to question number one should be obvious, right? The user include human being and also smart product, smart machine, and the smart system, all right? Then what are the needs from this user? The needs are the same. They want to have sensory data, all right? Then what should be the functionality of your product or your system in terms of sensor, network of a sensor, or network of sense, etc. So answer depends on the specific nature of the user. For example, vehicle may need a set of sensor, and the smart robot may need another set of sensor, all right? So answer to this question number three depends on the specific nature of the user, right? Then what should be the answer to question number four? Okay, the answer is to study this course. At the end of the study of this course, you will know the solution behind the design of your product or your system in terms of sensor or Internet of a Sensor, or Internet of Things, right? Then the third question that you may have in mind is about what are you going to study from this course. Basically, this course will cover the design principle behind the popular sensor in electric domain, magnetic domain, environmental domain, and intelligent system, all right? So this course also covers the basic detail about the physical world, the basic detail about the conceptual world, all right? And this course will also cover the basic knowledge for you to handle or to deal with or to cope with the randomness in the physical world, and also for you to understand the nature of fuzziness in the conceptual world. All right. Then how to apply the learned knowledge from this course. So this slide basically shows you the general guideline. Okay. So you should be able to apply learned knowledge by following these two key steps. Step number one is to transform the value of a physical quantity on the measurement into readable value, right? For step one, you may face some physical quantity which should be enough for you to make use of a single front-end sensing element. However, in most cases, you may have to make use of this combination of front-end sensing element together with the back-end sensing element, all right? So that's for the first step. Then the second step is to do calibration. In this way, you should be able to make the output value to be exactly equal to the input value. And in addition, you could make the unit of measurement assigned to the output value to be exactly equal to the unit of measurement from the physical quantity under the measurement, right? So here you understand that we should ignore the unit of measurement associated with the internal value, which are the output from sensing element, okay? Because that unit of measurement are not important to us, okay? We just need to get their value, because through calibration process, then we can restore the right unit of measurement, right? So these are the guidelines for you to follow in order to learn the knowledge from this course. Now we are ready to study today's lecture. So today's lecture is about the measurement of force, and the force is a very important physical quantity in mechanical domain. Therefore, it is important for us to do a review about the physics behind force. Then we will study the indirect way of computing force and the direct way of measuring force, right? Force is a very important physical quantity in magnetic domain, and especially through the use of the force, we could achieve human-robot interaction, human-computer interaction, or robot interaction with its work environment, all right? And this video shows you the typical example of human-robot interaction with the use of force, all right?
The object. Okay, see that naturally present, and even this kind of thing. Okay, a very odd shape one. Like that way, and square box, stuff like that. So, 한번 다시 해볼래? You may feel some graving force. Just try to. Okay. Let's try. Yeah. I will show you. Okay. Yeah. Different move. So here's. Okay. Okay. Now this will be handshake move.
But the grabbing is very tight.
Yeah, and if you put your palm like this way, it will grab. Okay, would you try? Anybody would try? Just okay, take your palm like this way and just wait. Okay. Yeah, naturally. Yeah, move. Try to move up and down, just slowly. Okay. There's a full stroke sensor here, so you just follow your movement. The natural. Okay, try. Yeah, here. Yeah. 5 minutes. How do you feel? Very so
Yeah, it's not so hard.
Yeah.
Try to
Follow because you naturally make the form according to the shape. Yeah, that's perfect. Right, this figure is missed. Okay, yeah. But naturally express.
All right. Then this video showing you the typical scenario of doing human-computer interaction with the use of force.
At Paratech booth with John Stark. Hi, John. I'm Red Doshi. Nice to meet you.
Great to meet you. How are you?
Good. How are you?
Great.
Can you tell us what you have here at the iZone today?
Sure. So Paratech has created a nanoparticle semiconductive ink that, when placed between two electrodes, front electrode here, back electrode here.
Yeah.
The white ink is our quantum tunneling composite.
Okay.
That when you press on it, it measures force.
Oh, very cool.
So
very cool.
Changes in conductance in relation to how hard you press on it. The material offers some advantages in that it's very simple to integrate, but also very sensitive. And used in a couple of different structures, you can do things from put it in a mobile device, put it in other sensing controls with buttons, remote controls, even
cool.
a drill.
Awesome. That's sweet. So if you look at the keyboard application, right, could you design a keyboard such that if you hit it hard, it makes the letter capital? And I mean, this one of the things you do today with the keyboard is if you're trying to have capital letters, you're
Absolutely. And this is actually, this product right here is designed for a keyboard, so that you have spacing, so you can really see good definition between keys, even when they're close together. And then if you push between the two, you can see a relative change in difference, right? So even if your thing's pretty close together in a very wide resolution, you can do that. Now, in other instances, you may want to integrate something with much higher resolution, so that if you move your finger just a little bit, you can use navigation. So one of the things that we've done, and I'll let Themis here describe this, is we've made an active matrix sensor. So here you have 24 by 50. Here you have 40 by 40, 80 by 80.
I see.
Very high resolution.
And this is run in an active matrix?
Yes. So you're measuring each individual sensor as opposed to passively scanning.
Got it.
So if you look at sort of the resolution here, right? Versus resolution here, look at how much resolution I can get. So now if you think about this, taking either your finger or a very thin, ultra thin joystick and being able to do very precise movements with just changes of your finger movement from side to side and around, you've turned your finger into a very high resolution joystick. Right? The nice thing is this stuff is bendable. Right? And it works when it's foldable. So if you look at this, I'm folding the sensor. No signal. But watch this.
That's excellent. So it looks like the possibilities that could be endless. So tell us what kind of applications you're targeting now.
So we're here at SID. We're targeting displays here. Right. So putting it behind curved displays. And we have one of our curved displays at the BOE booth. Their force sensing over there is our technology. And so it fits behind curved displays, also OLED. You have a display that's now deformable. You can put pressure through it, and you can sense that pressure through the deformation of that display. And that takes the advantages of having a flexible display and doing something with that. Capacitive doesn't. Capacitive's a great technology, but it's one of those things that when you're looking for positive force sensing, this is something we can add to the mix.
Excellent. Can you tell us a little bit about the power consumption for the technology?
So the great thing is it's very low power consumption. So, and this is where I'm going to defer to you a little bit because I'm trying to remember the numbers, but in its off state, right, it's virtually zero, right? Because it's an open circuit.
Yeah.
Right. But then when you press on it, you're creating the circuit. We're talking about microamps of use to when you're engaging the entire circuitry, a milliamp.
Got it.
Right. So it is very important to have force, okay, in order to support many applications. Okay, now we quickly go through the physics behind the force. Okay, the first knowledge or information for you to know is about the change of the state of linear motion. All right. So force actually is the root cause behind the change of the state of linear motion. All right. When we apply net force on the entity, then this net force will produce acceleration. Then acceleration will change velocity. Velocity will change position. All right. So it's quite straightforward to understand. And here is an example. For example, we do not want to change the state of the motion of this aircraft in the vertical direction, then we just make the net force in the vertical direction to be zero. Okay, maintain the state of the motion in the y direction. All right. However, we may want to change the state of the motion in the horizontal direction. Therefore, we make the net force in the horizontal direction not equal to zero. All right. So by controlling force component, we should be able to control the state of the motion of a rigid body. And in the physical world, okay, force could exist in many different ways. For example, we have a contact force, we have a field force, we have an induced force. All right. So now I'm going to show you some example which will help you to understand what do we mean by contact force, what do we mean by field force, what do we mean by induced force, right? For example, here you can take action of pulling an object, pushing an object, and pulling an object, right? You can work on the surface of the object, then there's an interaction force between the foot and the ground. Then in all these situations, basically, we make use of contact force, all right, to achieve these kinds of behavior in the physical world, all right? And here is also another example of contact force, okay? So inside the water, we may have a flow of the water, and this flow of the water may interact with a rotating device, all right? Then there is a contact force between the flow of the water and the rotating device, all right? And here also, we may have an object flying inside the flow of air. Then between the flow of air and the flying object, there is a contact force, right? So these are the typical examples, right? Then how about the field force? The most popular field force to us should be gravitational field force, because we experience the existence of such a field force every second, right? And then basically you understand the principle is very simple. As long as you have one pair of two masses, then there is a gravitational force exists between these two masses, right? And this force is proportional to the masses of these two entities and inversely proportional to the distance square between these two entities, right? And the G is just a coefficient, all right? And also, for those of you, if you could remember the lecture about the study of measurement of voltage, right? So we have a study, or we have done the revision about the electric field force, right? And we understand for a pair of like charges, then there is a repelling force, okay, between them. For a pair of n-like charges, then there is an attracting force between them, right? And this interaction force is proportional to the charges of this pair of entity and inversely proportional to the distance square between these two charges, all right? And in front, we have a coefficient, okay? And the 1/4 pi epsilon 0 is equal to this value, and this value is quite easier for us to remember, 9 times 10 raised to the power 9, okay? Quite easier to remember, all right? And then the third type of popular field force should be magnetic field force, all right? So for example, if we have electric charge flying inside the magnetic field, then the motion of the electric charge is equivalent to current. Current means what? Flow rate of charges. Okay, you remember? So when charge fly inside the magnetic field, then there's an induced force F, and the F will produce a centripetal acceleration that make the charge to undergo circular motion if there is no constraint of a conductor, because the charge is free to move, okay, in a three-dimensional space. All right, then in this case, the charge will follow a circular path due to the magnetic force induced on the charge, right? And the equation should be equal to Q times V times B, right? Because Q is amount of charge, Q times V is equivalent to I, current, right? So it's quite straightforward. And in case if let's say we restrict the charges inside conductor, so you cannot exit the conductor, then the entire conductor will experience, okay, or receive electromagnetic force, right? And this force is proportional to the length inside the magnetic field, proportional to the current which flow inside the conductor, and proportional to the density of a magnetic field, all right? So this is a quite straightforward equation, all right? And then, how about the induced force? The popular one should be centrifugal force, because I guess every one of you have had experience of taking buses or sit inside a vehicle, okay? And then you will see when vehicle follow a circular path, then your body will experience a centrifugal force, which will move your body away from the center of a circular path, right? So it's like in this situation, we have a passenger, okay, sit behind the vehicle. When this vehicle follow a circular path, then centrifugal force will push the body of this person away from the center of a circular path, okay? So, and the centrifugal force is proportional to centrifugal acceleration. Then what is a centrifugal acceleration or radial acceleration? So radial acceleration is proportional to circular velocity square divided by radian of a circular path, right? Once we know the radial acceleration, then we can calculate what should be the centrifugal force, all right? So it's m times a. Then for this example, the question tells you the radian of a circular path, the mass of this person, and the circular velocity is this one. So we must convert the circular velocity into the basic unit of measurement in terms of meter per second, all right? So once we know V, then we can calculate A. Once we know A, we can calculate the centrifugal force, right? So it's quite straightforward computation, right? And another example of induced force is called Coriolis force, okay? For those of you who have studied robotics, okay, when you study the dynamics of robot, automatically you must consider Coriolis force, because robotic arm may undergo linear motion and the rotary motion, okay? When there is a combination of linear motion and the rotary motion, this combination will induce this Coriolis force. And this is a discovery made by this French engineer with the name of Coriolis. This is why we use his name to name this force. So this is induced force by the combination of linear motion and the angular motion, all right? And this force is a vector, okay, which is equal to the cross product between the angular velocity vector and the linear velocity vector. Okay, so this is the convention that we put the negative sign in front of it. Then this force is in this direction. So actually, omega times v is pointing, in this case, is pointing toward the y-axis. Then negative, this one is pointing toward the negative y-axis. All right. So, and when we apply this knowledge, immediately you understand. Okay, if we shoot the object directly toward the north, actually the object will not land exactly in the north point. Okay, so there's a deviation towards the right-hand side. Therefore, we must shoot this object slightly towards the left-hand side in order for it to land exactly in front, okay, in the south, in the north. All right. Similarly, if we shoot an object towards the south, all right, we should aim slightly toward also toward this side, okay, the left-hand side, in order to make this object landed exactly at the location in the south, right? So this is the experience, okay, for us to follow, right? Okay, so that's all about the basics of force. Okay, then with this knowledge, then we are ready to do indirect measurement of the force and the direct measurement of the force. Indirect measurement of the force means a computation of the force from the knowledge about the related physical quantity, right? So we take example from a previous lecture. So in the previous lecture, we have studied all these equations. Now our focus is what should be the force F if we want to produce acceleration for the mobile base and produce acceleration of the ball in the x direction with this amount of value. For example, we want to produce this amount of acceleration by the mobile base, this amount of acceleration by the ball in x direction. Then what should be the force applied to the mobile base? So then this is a calculation. Okay, how to obtain this one? So basically from free body diagram, okay, of mobile base. So in the horizontal direction, we only have two forces, F and T times sine theta. Okay, T times sine theta is the force component of the tension force in the x direction. Then the net force should be equal to F minus T times sine theta. Okay, so and then for this ball, what should be the net force acting on the ball in x direction? So then in this case, there's only horizontal component from a tension force, right? Only one component. So it's T times sine theta. Then this one will contribute to the acceleration of the ball, okay, by this mass, okay? Then acceleration of the ball with respect to the ground, okay, should be equal to acceleration of the mobile base plus acceleration of the ball with respect to the mobile base, right? So then we have this equality. Then this equation plus this equation, then you should be able to get this equation. Then this is the way for us to calculate F if we have the intended acceleration for the mobile base and the intended acceleration of the ball in the horizontal direction with respect to the mobile base, right? And then what should be the tension force inside the rod which link the ball and the mobile base? If we want to know the value of the tension force, then we directly apply this equation, all right? Both sides divided by sine theta. Then we get the T equal to this formula, right? Then from here, we can directly calculate, okay? What should be the tension force inside the rod which link the ball to the mobile base, right? And then in this example, okay, if let's say we know the mass of a point A, the mass of a point B, then we know the distance between ball A and the ball B, and what should be the gravitational force, okay, between ball A and the ball B. So then we directly apply this formula because we know the mass of A, mass of B, we know the distance between A and the B. Therefore, we know everything, okay? Then we can directly calculate what should be the gravitational force. Then in this case, for example, we know the position of 3 charges, okay? And also we know the value of these charges. Then we should be able to know what should be the electric force acting on charge 3 by charge 2. So F23 means force acting on charge 3 by charge 2, right? So if we know the distance between charge 2 and the charge 3, then we directly apply this formula, right? Then from this drawing, we know the distance x coordinate of Q3 is equal to 5 meters, y coordinate of Q1 equal to 5 meters, and the y coordinate of Q2 is equal to -5, okay? Charge 1 equal to -20 micro coulomb, okay? And the charge 3 equal to 50 micron coulomb, right? And charge 2 is equal to 40 micron coulomb, all right? So therefore, we just put in the value, then we should be able to calculate the electric force acting on Q3 by Q2. And in this case, the distance R23 is equal to square root 5 squared plus 5 squared, okay? So it's quite straightforward, all right? And then how about the magnetic force? For example, if let's say we have a conductor or wire, okay? Inside this wire, there's a current of I, which is placed inside this magnetic field. Then in this case, if we know the length of this wire inside magnetic field is equal to L, and then we can calculate the force, okay, received by this wire, okay? And if we know the density of a magnetic field, right? So it's quite straightforward for you to calculate F, right? Then in this case, it's also quite straightforward, okay? Now, if let's say we know a charge of -10 coulomb enter magnetic field at this speed, right? So this should be the once the charge will undergo circular motion, then this should be circular velocity, right? And then we know, okay, due to the radial magnetic force, the magnetic force will produce radial acceleration. Then the charge will follow a circular path, and the radius of this circular path is 2 meters. And the mass of the charge is 0.01 gram. Then what is the magnetic force? And what is the density of magnetic field, right? So magnetic force should be equal to the mass times radial acceleration. Radial acceleration is equal to circular velocity squared divided by r. Okay, so we know all this value. Then we put in the value, we should be able to get the answer about the magnetic force. All right. Once we know magnetic force, so we know that the magnetic force is proportional to V, proportional to Q, proportional to circular velocity. Then B should be equal to F divided by QV. Okay, we know Q, we know V, we know F. Then we should be able to calculate B. Okay, so B is equal to this value. Unit of measurement is Tesla. All right. So, and then in this situation, now we have 2 parallel wire. Okay. In wire 1, there's a current I1. In wire 2, there's a current I2. And the I1 will produce magnetic field. And the density of this magnetic field is a function of a distance from the wire 1. Okay, perpendicular distance from the wire. All right. And then we have this equation. If wire 2 is placed at the distance r from wire 1, then the force, okay, received by wire 2 should be proportional to the current I2, proportional to the length inside the magnetic field, and also proportional to the density of magnetic field produced by I1. Okay, then we substitute B with this result. Then both sides divide by theta L. Then this means what? This is a magnetic force per unit length. Okay, so it's proportional to I1, I2, inversely proportional to the perpendicular distance between these 2 wires. All right, so it's quite straightforward formula for you to use in order to calculate the force per unit length, right? Then how to calculate Coriolis force? Then this is just a simple example, all right? And we know that Earth will make one round rotation every 24 hours. Therefore, we can calculate the angular velocity of the Earth, which should be equal to 2 pi divided by 24, because 1 hour have a 60 minute, 1 minute have a 60 second. Okay, so this is just to do the conversion of a unit of a measurement. All right, and the Coriolis force should be equal to 2 times m times velocity in the y direction, because we shoot this object, okay, in the vertical plane, okay, which contains the y-axis. Then along the y-axis, there is a velocity component, which should be equal to the initial velocity v0 times cosine theta, theta equal to 50 degrees, all right? So then this should be the linear velocity along the y-axis, right? So you put in the value, then we should be able to determine this force, and this force is in the x direction, okay? Then this force will produce this acceleration in the x direction, right? And when the ball fly in the air vertically along the z-axis, it will undergo motion with a constant acceleration. This acceleration is equal to g equal to 9.8. And in physics, we know that when we shoot an object, then the object will fly up, then fall onto the ground. Then the traveling distance, actually, we just apply this formula. Traveling distance is equal to 2 times initial velocity divided by g, okay? So initial velocity in the vertical direction is equal to v0 times sine theta, right? So 2 times initial velocity divided by g, then we can calculate the traveling time, okay, in the air, okay, is 1.56, right? Then in the x direction, so you will travel the same amount of time, okay, when you hit the ground, all right? Then during this period of time, what should be the displacement along the x-axis? So because in the x direction, the object will undergo motion with a constant acceleration. Acceleration is equal to this one in the x direction. Then the displacement should be equal to 1/2 at squared. So this is a standard kinematic equation with motion of a constant acceleration. All right. So we know the time, we know the a, then we can calculate, okay, this displacement along the x-axis, okay? So actually, you will see this is a very small number, right? So that's about the typical way for us to do indirect measurement of a force by computation, all right? Now our focus is to do direct measurement. Then what should be the physical principle for us to follow in order to design sensing and the measurement system for force, right? First, let's watch this video, and this video show you this popular force torque sensor in the market. And from the video, you will see the detail about the design of the sensor, all right? So actually, this is a hybrid sensor, okay? And we will come back to study the detail of force torque sensor in the next lecture, right? So here, I just show you this video for you to understand, okay, how to measure force and the torque together, all right?
We're scientists, right? That's our job. And so data is everything, and reliable data, repeatable data, that's paramount. And so if we have a sensor we can't trust, it undercuts the whole process. So we need to have data we can trust, and we have sensors we can trust.
That quality has to be perfect if we're depending on the robot to do its job correctly every cycle, day in, day out, year in, year out.
One of the things that makes robotics really function is repeatability or precision. What the force torque sensor from ATI gives us is both accuracy and repeatability.
The force torque sensor is a device that uses silicon strain gauges and converts mechanical loads into forces and torques, and it measures simultaneously in all 6 axes, force XYZ and torque XYZ. When you look inside the ATI force torque sensor, you can imagine it resembles a wheel with an outer wall, an inner hub with spokes or beams connecting them. Each beam has 4 silicon strain gauges that function in pairs to form half bridges. The output of the transducer is 6 channels of strain gauge voltages. The output is digitized and then converted to force and torques through a matrix calculation. ATI uses very sensitive silicon strain gauges to maximize gain, greatly reducing signal noise. The high gain in the strain gauges allows the beams to be extremely strong, providing very high overload protection. Proprietary bonding methods used during the mounting of the strain gauges greatly reduces hysteresis, which can be a problem for load cells.
The benefit of using a force torque sensor versus a single axis load cell is that you get a complete picture of everything acting on that transducer instead of just one snapshot of a measurement.
The ATI sensor can measure loads that are applied in any orientation on any axis. ATI force torque sensors can withstand overloads between 5 and 20 times the rated measurement range.
As a robot company, we have to be ahead of the curve, or try to be ahead of the curve. The good thing about ATI is they are ahead of the curve. Their force torque sensors are rated well beyond what the robot is spec'd at for payload. Let's say, for example, communications protocols and buses, ATI always seems to be right on line, right on track with what the industry needs at a particular point in time. So we don't really have to spend a lot of time asking ATI for features and functionality.
Our customers all have different environments where they need to use our sensor. So we have developed interfaces to work in every one of them, whether it's NetFT, which will communicate Ethernet data, or DAC-FT for connecting to data acquisition hardware, or the controller FT for standalone operation, and even our newer wireless FT and EtherCAT FT.
This product is being used in every major university in the United States and throughout the world. It's also used in every major manufacturing facility around the world.
The force torque sensor allows them to provide robots with a sense of touch, a sense of feel, that allow them to do applications normally done only by humans.
The most important thing force torque sensing gives us is the ability to open up the robot to other applications where we normally wouldn't have that ability.
Some of the more common applications for force torque sensors are product testing, life cycle testing, control of robots for surgery.
The robotics technology with the full 6 degree of freedom control gives you a lot of freedom that you never had before, because you need to be able to measure 3 forces, 3 torques to get the full loading state of any joint. And that's true for any joint. Once you establish that, you've established the full loading state of any specimen of any joint you want to do.
The coolest thing by far that the force torque sensor is being used for are groundbreaking applications, doing things that no company has ever done before. When we work with our space-related customers, or we work with people doing microsurgeries, things that haven't been invented yet, and we're able to be part of that process and go through the journey with them to develop their product. Really, whatever the customer needs, ATI is able to provide.
So the support I get from ATI is really great. They have all these products, so it's really nice. That's kind of a one-stop shop. So we're using ATI and have no reason to change. It's a good product, so we keep using it.
Coming from manufacturing myself, I know the importance of reliability and uptime. When we order a product from them, everything comes complete. Software, cables, hardware, take them out of the box, and we're up and running in 20 minutes.
We like using ATI force torque sensors here at ABB because of their robustness, first of all. They are proven, they've been validated by us and by the customers. Customers know them by name, they have a reputation.
Our trust in ATI has to be the highest possible because the quality and performance of the ATI product and its reliability is a direct reflection of how well our robot can do its job each and every time. And ATI is absolutely a critical part of that.
With the continuing innovation with ATI, their engineers at the facilities, they are not stopping at what they have today. They're continually looking to meet and exceed customer expectations today and for tomorrow's use.
Reliability of the force torque sensor is extremely important to ABB because our name is on that robot. We have to have very reliable end-of-arm tooling. And ATI gives that to us with their force torque products.
All right. So then we want to know, okay, what should be the for us to follow in order to come out the design solution for the measurement and the sensing system for force. All right. So here we just list down the popular principle. Of course, there may be other principle. All right. First of all, for example, force acting on special material could produce a voltage. All right. Then this animation basically showing you this scenario. Then we can leverage on the use of this type of sensing element to guide the design of measurement and the sensing system for force, right? And the second principle is for us to make use of this property in which force can cause a mass to have a deformation. Then when there's a deformation, this deformation will make, for example, a strain gauge to change the conductance or resistance, all right? Then by measuring resistance, then we should be able to measure, okay, force, all right? And the third principle is to make use of this property in which force can cause a mass to undergo displacement. And when this displacement change the relative position between two parallel plates, then the capacitance will change. Okay, so this is another the design principle for us to follow. All right, so here we will basically focus on the use of change of resistance to guide the design of force sensor, because in the video you will see that is a typical product which make use of this principle in which force produce deformation. Deformation cause the change of resistance, right? So these are the popular principle for us to follow, right? And then before we look at the automatic way of undertaken measurement and the sensing of a force, and in our daily life, I guess some of you, if you frequently go to the market to buy vegetable, to buy the meat, or to buy other items, right? So you know this manual scale, okay, for us to measure the weight of vegetable, measure the weight of okay, a different item. So you see, we have a hanger. Inside we have a spring, right? Then we have a pointer. We have a calibrated scale, all right? Then we have a hook here for us to attach object on the measurement. Then we can easily verify, okay, whether this vegetable is 500 grams or 1 kilo or whatever, right? If you carry this scale, then you should be able to verify the weight of a purchased item, right? So, and then, for example, okay, we have this equality because for a spring, the elastic force is proportional to the displacement, okay, with respect to the neutral position. Then, how about variation? We can also have this relationship, right? The variation in the elastic force is equal or proportional to variation in the displacement, and this is a typical scenario, okay? So once we put the object on the measurement into a liquid, then you will see there's a buoyant force, all right? And the deeper it goes, then the buoyant force will be higher, all right? And if we put additional object here, you see this is an additional object here, then the buoyant force, okay, is not sufficient to overcome, okay, the weight of this additional object, okay. Then you will see the weight of the variation of force, elastic force will occur, right? So this basically showing you the typical scenario, okay. When this one is inside the air, then this will not produce a buoyant force. Once you put inside here, because this object will also expel the liquid. Okay, the buoyant force is equal to the weight of the water or liquid of the same volume. Okay, as this object, right? So then the buoyant force will appear. Then you see there's a variation in the elastic force, right? So this is the design principle which make use of this principle. Okay, force will cause a mass to undergo displacement. Okay, then we can design a measurement system for us to undertake manual measurement of the force, right? However, our focus here is on the design of automatic measurement and the sensing system. All right, then how to use this principle, okay, of a conversion from a force to voltage, right, in order to guide the design of automatic measurement and the sensing system for force, right? In this case, if let's say we have a sensing element which allow us to directly convert the value of the force into value of a voltage, then we just use this blueprint because all the microcontrollers are programmable digital sensor of a voltage. Okay, this is because we can have a digital counter to predict the digital value. For each predict digital value, we convert it into corresponding analog voltage. Then we do the comparison between the predict voltage and the input voltage. When there is a perfect match, then this comparator will output a stop signal to stop the prediction. Then the actual value inside the counter is equal to the digital output, okay, which correspond to the value of voltage, right? Then in this case, we just need to add in this module, which will transform the value of a force into value of a voltage, okay? So, and this video basically showing you the use of such a device, okay, in practice.
This is a piezoelectric element that we obtained from a buzzer like this. Here we have the piezoelectric element connected to a voltage meter. When the element is pressed, a voltage is produced. We can see that voltages of up to 20 volts are obtained.
Right, so we can just use this sensing element to implement the first module here, then done already. So you have automatic measurement and the sensing system for force, right? So this is one solution, okay? Then second solution is to make use of force to resistance conversion in order to guide the design of automatic measurement and the sensing system for force. Then in this case, we need to first undertake conversion from force to resistance, then from resistance to voltage, right? So we have already studied the detail about the conversion from resistance to voltage. Therefore, here we just want to know how to do conversion from force to resistance, all right? Then in this way, we could leverage on the use of a microcontroller to implement the automatic measurement and the sensing system for force, all right? Then next question is how to do force to resistance conversion. The answer is to use the strain gauge, all right? So when the strain gauge is placed on the beam, when the beam is not undergo any stress or external load, okay, then you have a nominal value for resistance, all right? If there is a compression, okay, on the compression or on the tension, okay, so then here is the motion or the load of the beam, okay, will make, for example, strain gauge to under compression. Then in this case, the resistance value will reduce, okay? And this is the load acting on the beam will make the strain gauge undergo tension, okay, expansion, all right? Then in this case, resistance value will increase, all right? So it means external load due to the force, applied force, will make the resistance value from the strain gauge to vary, okay? Then we can do the conversion from the force to resistance value, okay? So this is just a simple solution. Then how to do the conversion from resistance to voltage, okay? The universal solution or popular solution is to make use of this Chris circuit, okay? So in this case, R4 is resistance on the measurement. R1, R2, R3 are resistor with no value of resistance, all right? So when the resistance of R4 change, then the voltage between point A, point B will change, all right? Then what is the equation which describes the voltage change? Then here you know, okay? From the left branch, the VA is equal to input voltage divided by the total resistance, okay? Then times resistance of R3. Then in the right branch, and the voltage at point B is equal to Vs divided by total resistance times resistance of R4, all right? Then VA minus VB is equal to this one minus this one, all right? So then we just name this one as a voltage V. Then from this equality, both sides divide by Vs. Then we have this equation. Let me just shift this one toward the left-hand side. Then V divided by Vs toward the right-hand side, okay? Then this one will equal to this one, okay? Then we can name this as a K because R1, R3, R1, R2, R3 are known, okay? So V is on the measurement, so we just, okay, name this as a K, right? So then, okay, we should be able to, from this equality, then that means we can calculate K, because when this change, so we will get the value of K. Then K is equal to this one, okay? Then from this equality, then we can easily solve for R4. Then R4 equal to R2 times K divided by 1 minus K, all right? So from here, you will see when there's a variation of R4, okay? Then there should be a variation of a K. When there's a variation of a K, then there's a variation of a V, right? So this is the way for us to determine the voltage, okay, from the value of R4, right? So when R4 change, then V will change, all right? So these are the equation behind this conversion, resistance to voltage conversion, all right? Okay, and this video show you an example of implementation, okay? So we have this, it's like a sensor which will output variable resistance, then okay, interface it with microcontroller, all right?
So I'm going to show you how to connect a FSR to the Brain Junior. FSR is a force sensing resistor, and it works like a button and like an analog at the same time. So this is something that you'd see in like a drum controller or a bass controller, anything that has velocity sensitive pads. The harder you press, the more velocity, and when you let go, the velocity goes down. So it acts like an analog control. In essence, it goes from 0 to 127, but instead of moving a controller, you're just pressing, and it's registering your force. For this example, all I need is a Brain Junior, an FSR pad, 2 jumper wires, and a 10K ohm resistor. The nice thing about the Brain Junior is we designed it to work with these cables that can easily be plugged and unplugged, so you can do completely solderless connections. All right, to get started, I need to take my FSR and plug it into the brain. I'm going to be using analog connections here since this is in, it sends out an analog signal. And the way this FSR also has these jumper connections here, so I can easily plug it in. So I'm going to go ahead and connect one of these lines to the inside, which is my voltage. Connect the second line, and you can do this Either way, it's just going to register your value different. So there's no right or wrong way to plug these two in here. You just have to make sure you're following this. And I'm going to plug this into the wiper, which is the center connection. Before I do that, I'm going to take this 10K ohm resistor and I'm going to wire it in between the ground or the negative and the wiper. This is going to have to push this in a little bit harder because I'm trying to fit these two connections in here. But there you go. I have a wired FSR. Now, to make this work like a real FSR, what I'm going to have to do is go into my brain configure application. And what I'm going to do here is disable all the unused analog controls. There's 16 per brain junior. So I'm going to go ahead and disable all these controls. So I just have the one. And then I'm going to change the type from POT FSR and send configure to the brain. Now I'm going to open my tools window so you can see what happens when I press it. So you can see the harder I press, the more value it gives me. And this works just, if I was to connect the potentiometer here, it would give you the same readout. So depending on how hard I press, you get long or short presses with different velocities. So this is the Brain Junior FSR tutorial.
Right. So in the video, you may heard of this term, FSR, force sensing resistor. Right. So it's basically inside you can guess out there should be a strain gauge. Okay. When you apply external load as a force on it, then the resistance value will change. All right. Then we can convert that one into voltage and then voltage into digital value. Then after calibration, then you should be able to get the correct value. All right. So this slide remind you, okay, to remember to do calibration. Okay, because sensing element will only produce readable value. This readable value may have their own unit of measurement, which should be ignored. All right. So we just get this value. Then by doing calibration is to make ZI exactly equal to XI. In addition, then we can assign the unit of measurement of XI to ZI. All right. By ignoring the unit of measurement of YI. Right. So therefore, after calibration, the relationship between XI, ZI will follow this straight line, which is 45 degrees above horizontal axis, right? Then, okay, after calibration, then your measurement and the sensing system should be ready, okay, for doing testing, etc. All right. Then always remember, okay, try to do data acquisition in order to support this error analysis, because you need to do error analysis in order to know systematic error, repeatability error, accuracy, and in particular, hysteresis error. Then how to know whether there's a hysteresis error? Then you must increase the input, okay, get a series of reading, then reduce the input, get another set of reading. Then you calculate the error, then you do the comparison, right? Whether there is a gap or not. If there's no gap, that means no hysteresis error. If there's a gap, then your sensor has a hysteresis error, all right? So remember to do error analysis, all right? So that's all about this lecture on measurement of the force. So the key takeaway from this lecture is for you to understand the physics behind the physical quantity of force. And also the second key takeaway for you to know is the different way for you to do indirect measurement by computation. If you know the related physical quantity, then you can calculate the value of the force. However, our focus here is to know, okay, to apply, learn the principle in order to guide the design of a direct measurement and the sensor system for force. All right. So here, basically, we know we can make use of a sensor element which could directly convert force into the voltage. All right. Then second, the principle for us to follow is to do conversion from a force to resistance, then to do conversion from resistance to voltage. All right. Then in this way, we could leverage on the use of a microcontroller to support the implementation of a measurement and the sensing system for force. Thank you for your attention. I'm looking forward to seeing you in the study of the next lecture.